All right, and welcome back. Mr. Richardson here. And our final lesson in solutions, kind of a hodgepodge of solutions and some of the different properties that we see when we have a solution. So hodgepodge, we're going to talk about a lot of different things today. First one being the solubility of gases. So again, solubility means being dissolved, and now we're going to be looking at gases. So far, all the math we've done, all the calculations we've worked with, all the examples we've looked at have been solids dissolving in water or other liquids dissolving in water. But gases could be the solute as well. If you've ever opened a can of soda, a 2-liter soda, you've heard that. Well, that's gases that are dissolved in the soda and are escaping. There's a picture, some CO2 that is dissolved in this solution. If you were to have a closed container, so we've got the beaker or jar, it's got a lid on it, those gas particles are going to be constantly moving in and out of the solution, back and forth, back and forth. The higher the temperature, the more gas particles are going to escape the solution and go into that open air area. If you left the lid off, those gases would escape and wind would blow them away, and that's when your soda goes flat, is because you are constantly losing gases and none of them is going back into the solution, and eventually you have no more carbon dioxide in your soda and your soda's flat. So higher temperatures result in lower solubility of gases. And that leads us to Henry's law. At a given temperature, the solubility, which is represented by the letter S of a gas, and a liquid is directly proportional to the pressure, represented by the letter P, of the gas above the liquid. And Henry's law, again, they're just directly proportional. So S1 over P1 is equal to S2 over P2. Quick example of how that works. If 0.85 grams of gas at 4 atmospheres of pressure dissolves in 1 liter of water at 25 degrees Celsius, how much will dissolve in 1 liter at 1 atmosphere of pressure and the same temperature? Again, I like to list out my variables. If we're using Henry's law, we're going to have an S1, and that is our 0.85 grams per liter. Our P1 is 4 atmospheres. Our S2 is what they're looking for, how much will dissolve per liter. And this is how much is dissolved per liter, so how much is dissolved per liter. And our second pressure is just 1 atmosphere. So there's our formula. We want to isolate our variable. We're looking for S2. We'll multiply both sides by P2 in order to find that. Cool, we can plug in our variables and we can solve for S2 at 0.21 grams per liter. All right, as I mentioned, it's kind of a hodgepodge of information today. So next up, we have electrolytes. You've probably heard of them. Gatorade likes to advertise all the time that they have electrolytes. Well, to be honest, there's nothing terribly special about electrolytes. They are simply compounds that go into water, dissolve, and conduct an electrical current. So here is sodium chloride, or potassium chloride, I guess, in this example. We have positive and negative charges. Those ions have come apart, and so now you could conduct an electrical current. You could push electrons across these negatively and positively charged sides. Something that is not going to dissolve in water, for example, ethanol, has no charge. You cannot push those electrons across, and therefore it is not an electrolyte. So what the notes are talking about here is take a look at sodium chloride, which is definitely an electrolyte, a very strong electrolyte. When we dissolve sodium chloride, so here's regular old table salt. You could have it in your hand. It's white. You throw it in some water, and now you get Na+, which is aqueous, and Cl-, which is aqueous. These two dissolved particles. So 1 mole of salt would yield 2 moles of aqueous molecules. And that's going to be important here in a couple of slides. 1 mole of NaCl, but 2 moles of dissolved particles. Now that's different from a molecule such as sugar, C6H12O6. Sugar does not come apart in water, does not dissociate like sodium and chloride. We do say it dissolves in water because when we look at sugar, when it's a solid, it's all clumped together. It has enough positive and negative charges that it will stick together. When we throw it into water, one C6H12O6 particle will come apart from another, but it doesn't dissociate like sodium and chloride ions. So, again, why is this important? 1 mole of sugar is only going to yield 1 mole of aqueous molecule. It's not going to dissolve and split in half and double like sodium chloride. All right, brings us to colligative properties. Colligative means collection, and here is the idea. We hopefully are all familiar with the basic properties of water. It boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. It has a density of 1 gram per 1 milliliter. It has a specific heat of 4.184 when it's in its liquid state. We'll talk about that next chapter. But colligative properties talk about how those properties of water change when we dissolve something in it, when we have a solution. So the water and the solute are going to have different properties than just the water by itself. So some of the properties we're going to talk about and work with, vapor pressure, which is lowered, boiling point is elevated, freezing point is depressed, which means lowered, and osmotic pressure, which we'll look very quickly at. Hopefully you guys remember osmotic pressure from biology last year. All right, starting off with vapor pressure. So vapor pressure is the amount of pressure that is exerted and therefore how many particles are escaping. Water, even below 100 degrees Celsius, water is going to be going back and forth between the liquid and the gas phase. There will be some particles that are going to travel fast enough to turn into a gas, a water vapor. As we start to add solute, that's what the red dots are in the second picture, we are decreasing the surface area that the water has with the gas up above. So a smaller surface area means a smaller ratio of water molecules that are able to get to the surface and therefore escape. So having solute particles is going to lower the vapor pressure. It's going to make it harder for those water molecules to escape into vapor. So the greater the number of solute particles, the more solute you add, the lower the resulting vapor pressure. You, for some reason, want to make sure you keep a solution. Add some salt to it. Add more salt to it. Add more salt to it. Decrease the likelihood of it evaporating from you. Kind of leads us into our second colligative property, boiling point elevation. So liquids boil when that vapor pressure we just talked about equals atmospheric pressure. And for water, pure water, that's at 100 degrees Celsius. However, what we just looked at was as you start to add particles, more and more particles to a solution, the vapor pressure is lowered. This means that our boiling point is going to have to be higher. It's getting harder and harder for the liquid, in this case water. It's getting harder and harder for the water to turn into vapor. So it's going to take more and more energy to vaporize it. So you're going to increase the boiling point. At we do have a formula to figure out exactly how far we're elevating the boiling point. So here is that formula. You'll notice the letter I, that stands for the Van't Hoff factor, which represents the number of dissolved particles. Do you remember a couple slides ago when I mentioned how important it was that sodium chloride, 1 mole of sodium chloride equals 2 moles of dissolved particles? Well, that's that I value. So when I put sodium chloride into a solution, the I, the Van't Hoff factor, is 2. Because sodium chloride makes 2 particles. 1 mole of sodium chloride equals 2 moles of particle. Other factors you're going to need. Notice it's an italic M. It's molality of the solution, so always watch that. Then the KB, this is a given. We'll make sure we give that to you. There are different KBs for different liquids, so watch which liquid you're using. I'll have a table, I believe, on the next graph. And then also notice what we're finding here is the change in the boiling point, the delta TB, the change in the boiling point. Generally, they'll ask you, at what temperature will water boil? Do not leave this as your final answer. Keep in mind, water already boils at 100 degrees. So if you got a boiling point elevation of something like 5 degrees, you'd want to make sure you add that to 100 degrees. So your final answer would be 105 degrees. So you notice the formula here tells us the change in boiling point, not the new boiling point, just the change in the boiling point. So again, boiling point elevation, adding salt to water will make the water boil at a higher temperature. Perhaps you've noticed when someone cooks food, cooks pasta especially, they throw some salt into the water on the stove as they're bringing it to boil. It's a common misconception that the salt brings the water to a boil faster. That's not true. In fact, throwing the salt in will increase the boiling point. Therefore, it's going to take longer to bring that water to a boil. That water will take longer time to boil when you add the salt to it. The reason why cooks do this is that you now have a higher temperature of water once it does start to boil, and therefore you can cook your food a little bit faster. So if you've ever seen mom or dad or brother, sister, or whomever adding salt to water to boil, what they're trying to do is get the food to cook faster, not the water to boil faster. Again, here is the table. You would be provided with this on a test. We have a list of solvents. Again, water's the common one, but it doesn't have to be the only one. Here are some other liquids that could be used as solvents. Here is their normal boiling point. Again, with water, 100 degrees Celsius. Benzene's a little bit lower. Chloroform's quite a bit lower. And then here are the constants, the KBs. And water's is quite small compared to the other KBs. But pay attention to what your solvent is, what its normal boiling point is, and what its KB is. Here's an example. What is the boiling point of a 1.5 molal sodium chloride solution? That's nice of them. They already gave us our molal, so we don't have to do any conversions with that. So our KB, 5.512, molal 1.5, and then keep in mind NaCl, the Van't Hoff factor is 2, 1 Na plus and 1 Cl negative. So we plug our variables in, we find our delta TB, our change in boiling temperature, to be 1.536 degrees Celsius, and then don't forget, that's not the final answer. We have to add that to the 100 degrees at which water already boils. Our final answer, the new boiling point of this water would be 101.54 degrees Celsius. Another example. What is the boiling point of a solution that contains 125 grams of calcium chloride and 1,400 grams of water? Aha! They didn't give us the molality this time, so we'll have to find that on our own. still using water, so our Kb will be 0.512 degrees Celsius per molal, and our Van't-Hoff factor will be 3. Recall, calcium chloride is CaCl2. So when it dissolves, you're going to get 1 calcium and 2 chlorides. That's a total of 3 dissolved particles. So the Van't-Hoff factor is 3. Okay, we're going to have to solve for the molality. And molality is moles of solute over kilograms of solvent. We were given the kilograms of solvent, there that is, 1,400 grams of H2O. A quick grams to kilogram conversion gives us that. But we have to convert our 125 grams of calcium chloride into moles. We need moles on top. So we use a periodic table, convert grams to moles. We know our conversion of grams to kilograms, and we come up with a molality of 0.80449. And now we've got the information we need to solve with our equation. And I've CDU'd here, carry digits, underline digits. And I find my change in boiling point to be 1.2356 degrees Celsius. Again, just 2 digits, going back to the 1,400 grams of water. So I left me with 2 digits there. Again, I'm going to CDUD all the way till the end and end up with a change of 101.2 degrees Celsius. My new boiling point of this solution. The opposite of the boiling point, when we add salt to a watery solution or any kind of solution, we're actually going to depress or lower the freezing point. And this is the idea behind why we put salt on our roads. Keep them from freezing. We can make it a lower temperature, at which point that road will freeze, or that ice on the road will freeze. So in a solution, the solute particle interferes with the attractive forces, and it makes it more difficult for them to solidify, for them to all unite and form a solid. So again, here's pure water. And again, if it were to turn to solid, we would need all these water molecules to kind of get stuck into a crystal lattice. If I had salt particles, I look over here on the right, these green dots are my salt particles. They're going to disrupt the water-to-water interactions. So there are not as many water-to-water interactions. That makes it harder for the water to form the crystal lattice. And therefore, it lowers the temperature at which water will freeze. Very similar to our change in boiling point, we have a freezing point depression. The constant is negative, so you should end up with a negative value. So again, always subtract that from 0. Hopefully we all recall water's normal freezing point is 0 degrees Celsius. We still have our Van't-Hoff factor because it matters how many particles of salt you're putting into the solution, how many they dissolve into. Another chart, another table, again, make sure you guys take a look. Kf for freezing, Kb for boiling. The numbers are quite different, so make sure you're paying attention to that and know what type of problem you're working with. So you want to put some salt on your driveway. You have a choice between sodium chloride and calcium chloride. Which one would you buy to melt the ice? Now, that doesn't factor in any of the expenses here. But I would choose, assuming they're all priced equally, I would choose calcium chloride. It's going to have 3 of those Van't-Hoff factors, 3 of those molecules, 1 Ca2 plus and 2 Cl negatives, versus sodium chloride, which only has 2 solute particles. The colligative property we're looking at is the freezing point depression there. All right, how about a mathematical operation then? And very, very nicely, they gave us the molality, so we didn't have to do any math there. And these numbers came from the chart on the previous page. Our freezing point depression, 5.58 degrees Celsius. Don't forget, that's not your final answer. You need to subtract that from 0 degrees Celsius. And we find a new freezing point of negative 5.58 degrees Celsius. And so therefore, by putting a little bit of salt on our road, we can make it a colder temperature that ice or that water will turn to ice. Freezing point depressions. Another example. Hey, notice carbon tetrachloride dissolved in benzene. Interesting. All right, we're not working with water. When you're reading these questions, make sure to identify what it is you're working with. Carbon tetrachloride also is a covalent molecule, which means it's not going to dissociate into carbon and chloride ions. It's going to stay together. 1 mole means 1 mole. The Van't-Hoff factor will just be 1. Once again, we were not given the molality, so we had to solve for it. 12 grams of carbon tetrachloride over 750 grams of benzene. Our quick grams to kilograms conversion, we'll put kilograms on the bottom. And grams to moles, we want moles of solute on the top. I think it always helps to list what it is we're looking for. Molality is moles of solute over kilograms of solvent. We solve for this molality. CDUD again. We find a freezing point depression of 0.53248 degrees Celsius. You can notice I used a different KF also. I went back, I looked at the chart from a couple slides ago, and I found the KF of benzene. That's our solvent this time. Also, when I do the subtraction, my change in freezing point, I subtracted it from benzene's normal freezing point, which is not 0 degrees, that's for water. We're working with benzene, and I found this number on the chart a couple slides ago. My new freezing point for benzene, when it has carbon tetrachloride dissolved in it, be 4.95 degrees Celsius. Finally, a quick slide on another colligative property, and that's osmotic pressure. Me being a biology teacher, I always like to talk about this. It's so very important in life. So the idea is, on one side of the pipe here, we have pure water. On the other side, we have a solution. This is a semi-permeable membrane, meaning water can go through, but the salt particles, or solute particles, whatever they may be, cannot go through. Water is a very, very small molecule, just 2 H's and 1 O, much smaller than a lot of the other particles that might be dissolved in it. So we can make semi-permeable membranes. We can separate a pure water, from a solution here on the right. And osmotic pressure, is the idea that the water will travel through that membrane in an attempt to equal out the concentrations of the solution. Hopefully you guys worked with some osmosis with your cells last year. Very important that our cells floating around in our blood have about the same concentration of salts on the inside of the cell as the outside. This is why it's so dangerous to drink distilled water. Perfectly pure water, your cells have a lot of solutes in them. So if you drink perfectly pure water, that water is going to flood into your cells and cause your cells to pop. Not good. You've got a homework? Take a look. You will probably have to refer back to the charts earlier for your KBs and KFs and your normal freezing points. Those will be given to you on a test, so please don't memorize them. But take a look, see how you do.